this demonstration of the MOX Metrology Process Studio, or MPS as we like to call it. I'm Kurt Casto. I'm the designer of the MPS software architecture. MOX MPS is the technical part of the MOX system. It's used to design and execute the calibrations. There are two principal kinds of documents in MPS. Datasheets. These are the templates for calibrations that include the test points, specifications, instructions, and optionally automation scripting to automate the calibrations. And then there are calibration documents. These are the actual recording of measurement data performed during calibrations, and that data is saved as a calibration document. MOX MPS uses a Microsoft SQL Server database to store its data. Optionally, you can also save these as files. There are two ways to launch MPS, either directly or if you're using MOX CMS, when you go to perform a calibration within MOX CMS, there's an option to have it launch MPS with the appropriate datasheet template and everything loaded, ready to perform the calibration. However, if you don't have MOX CMS or you're just going to be designing datasheets or something like that, you can just launch MPS directly, which is what we're going to do now. So we'll click on its icon to launch MPS, and then we'll go ahead and log into MPS using our CMS authentication as a CMS user. If you want to perform a calibration in MPS, the first thing you'll want to do is open an existing datasheet template. And you do that by going up here to File, Datasheet Template, Open Template from DB, and this brings up our datasheet document selector. And then we can actually choose a datasheet using one of several criteria. We can look it up by model, manufacturer, description. A key thing about datasheets is that while you're working with them, you'll be saving them as files, but eventually you'll approve them into the database, assuming you have permissions to approve them. If not, you'll give them to somebody else to approve. And then once they're in the database, they can be used to perform calibrations. So we'll go ahead and just search by model number. So we'll enter 77. And then when I type something in and I either hit enter or click on the search button, it will show me all the data sheets that start with what I selected, or you can choose other things like exact match or contains. So if I select this data sheet, it loads the data sheet. This is the calibration channel editor, and it's asking me to provide a test number and an asset ID. Now, once again, if you're actually using MOX CMS, then you don't have to do all this process we just did manually. You would just launch the calibration from CMS, and then it would automatically open the appropriate data sheet and fill out all of the information here for you. I'm just going to go ahead and cancel this. We're not going to actually perform a calibration right now. Just going to show you some things about MPS. So there are two principal modes in MPS. There's the calibration mode, which you see here. It comes up by default. And then up here under mode, you can also come up here and select the design mode. And in the design mode, this is where we would actually construct the datasheet and all of its test points. And there are various tools in here to do that, but we'll talk about these tools in more detail at a later part of the demonstration. While you're working with datasheets, what you'll normally do is you will save them as files. So import, export to file. If you come back the next day and you continue working on the datasheet, you'll import it from a file. And then eventually, when the datasheet is completed, if you have the necessary permissions, or you can send the datasheet file to someone else that has the necessary permissions, and they can approve it into the database. When you do approve a datasheet, you would just go to File, Datasheet Template, Approve Template to DB, and then you can either approve it as a revision or approve it as a new document. Let's switch back to the calibration mode, and let's actually execute a calibration launched from CMS. This is CMS, and as I said, this is not a CMS demo. We're just doing what we need to do to demonstrate performing a calibration launch from CMS. This is the work order view in CMS, and I've got a work order opened here for a digital multimeter. So we're going to launch this calibration in MPS to actually perform the calibration. I right-click and I choose Launch MPS. This will actually launch the MPS application. MPS was launched, the appropriate data sheet was loaded, and it filled out the test number and the asset ID and the other make model information. So we'll go ahead and hit OK to begin that calibration. This particular data sheet is an automated data sheet, and you can always tell that because in the step number field here you see these teal regions. These are all places where I can start the automation scripting from. And you can also see the button up here to start the automation scripting. And we'll just actually start at the DC voltage test. The first thing I need to do is tell it about the calibration standard I'm using. Now this particular data sheet is set up with one calibration standard, a calibrator, and you can see down here below I have 4 different calibrators to choose from. So I'm going to go ahead and start with the selected Fluke 5522 calibrator. We'll enter the asset ID for that. And when I hit enter, if you're using MOX CMS, it will automatically go out to CMS and look up that particular asset ID and get the due date for me. And when I hit yes, you can see it fills in the due date. Once I've set up my standards, I can go ahead and just turn off this view of this workspace. And in MPS, your primary workspace tools are always on this right side, whether you're in calibration mode or design mode. I'm going to go to View, and then I'm going to uncheck the Developer Workbench. So it turns that off. That allows me to see more. As I said, this is an automated data sheet, and we're going to use that to record a couple of data points. We'll stop it after it records a couple of data points, just in the interest of time. Let's go ahead and hit our Run button, and this will start the automation script running. These are my instructions, and here's an image of how to actually connect the equipment. Let's hit Continue. And as I said, we'll just let it take a couple of data points, and then we'll hold it. And you can see this little status indicator over here just shows what it's doing. Mostly it's spending its time, waiting for stabilization and whatnot. I'm going to go ahead and hit halt. You can see as we were taking our measurements, our as found values were being filled in here in the datasheet template. And then some other information. This is a conformance diagram. And then in this channel status column, you see we've got this box that's divided into 2 halves. The top half is as found and the bottom half is as left, indicating that the green meaning that our as found values were in tolerance, and the white and the as left indicating we haven't taken or captured as left data yet. MPS is a multi-channel system. You can actually perform calibrations on multiple instruments at the same time. That would be applicable to something like thermocouples, where you have 3 or 4 thermocouples in the bath at the same time, in which case you can open multiple channels, and then you would see a set of boxes for each of those channels here. One of the key things about MPS is that you can change calibration standards at any time during the calibration. If we had gone through and taken all of our as-found data, we have 2 options after that. If everything was in tolerance and we're not going to adjust, then we could come up to copy as found to as left and just have it copy all of the as found data into the as left measurements. However, we're going to choose as left, and then I'm going to go back to View here, and I'm going to bring up my Developer Workbench again. And this time, we're actually going to choose a different standard to take our as left with, so I can illustrate a few things to you. For the as left data recording, I'm going to choose the Fluke 5500 calibrator. We select the 5500 here, and then we hit Use Selected Instrument, and then we're going to enter the asset ID for the Fluke 5100. Now, I should tell you that the Fluke 5500A really is a good bit less accurate than the other standards in here and is really not a good choice for this calibration. However, I have it in here for demonstration purposes because this is going to let me illustrate some other things. So let's go ahead and turn off our workspace view again. Let's come back up and choose our DC voltage tests. And now we're in as left mode. So let's collect just a few as left data points. Again, the same thing in the interest of time. We'll just collect a few points. And you can see as this is running, you can see the conformance diagram being updated as we go. And then this section over here, the tolerance percent, what this is, let me go ahead and halt this. This is just telling me the percentage of the tolerance consumed. So now we'll go ahead and bring our developer workbench back up, our workspace. And then I'm going to actually choose standards used, measurements made. This is going to give me detailed information about the measurements that were made for this test point. A key point in MPS is that it's largely test point centric. And what I mean by that is whenever I choose different test points, you can see that whether it be this section or this section up here or this over here gets updated with whichever test point I'm on. So everything is pretty much driven by the currently selected test point. One thing I want to point out here is if you notice this section at the top up here showing detail for our as found and as left measurements, but you'll notice a difference for our as found and as left measurements. For our as found measurement, we have our tolerance is not guard banded, but our as left tolerance was automatically guard banded. And this is again why I wanted to use that Fluke 5500 for demonstration purposes. Because of the 5500, you can see its TUR is only 2.5 to 1, and its PFA is above our target 0.8%. So MPS automatically guard banded it. And where you can see our as found measurement, our TUR was 9.7 to 1, and our PFA was only 0.39%. As I said about the 5500, again, in the real world, you wouldn't really use a 5500 with this particular calibration if you had these better calibration standards. But for demonstration purposes only, it lets me illustrate some things that I need to illustrate. Viewing the detailed information on the right over here for the measurements made, you can see we actually have two sections in here, as found and as left. And each of these is showing detail about that particular measurement. So for our as found, you can see the standards used, which was our Fluke 5522 calibrator, is specifically this asset with this due date. And then the TAR for this was 7.6 to 1, and the accuracy of the standard was 5 microvolts, specifically at 200 millivolts, our set point. And this is actually showing me which function and range of the 5522 calibrator was used, and even the specifications for that range. And we will be talking about where all this comes from a little later. For the uncertainty model, MPS has two items in the uncertainty budget here. It has the measurement resolution and the calibrator that's being used, in this case the Fluke 5522. One thing I should tell you at this point is that everything you see in the budget here was done automatically by MPS. It created these budget items and it's managing them. And if we were doing sampling, then it would automatically have an option to insert a type A budget item for the standard deviation of the samples. And we'll talk about sampling a little later, but if these test points were configured for sampling, say we wanted to take 5 samples, then another section would appear in here that would actually show the samples being taken and a graphic display of the sampling data. And then the mean value of the samples would be the measured value, and the standard deviation of the samples would be added as a type A budget item. in the uncertainty model. And then another section that you can see displayed here is risk. And in this case, we have our probability of false accept and our probability of false reject, total risk, and K, which is essentially our guard band multiplier. We're not guard banding, so it's 100%. In the as left section, it's very similar to the as found, except our calibration standard used was the Fluke 5500 calibrator, as opposed to the 5522 calibrator for as found. The accuracy of the 5500 at 200 millivolts DC was 15 microvolts as opposed to 5 microvolts. And then in the uncertainty model, very similar to the as found uncertainty model, except instead of having the 5522 calibrator automatically added to the budget, it added a budget item for the 5500 calibrator. For the risk, we guard banded. The method used was the ANSI Z540.3. MPS supports 3 guard band methods: the ANSI Z540.3, the RP10, and RSS. The ANSI Z540.3 method will guard band just enough to return to your target PFA. One of the things I hope you're asking yourself at this point is, how does it know all this? I told you that everything that you see in here is done automatically by MPS. We didn't have to manually edit the uncertainty budgets. We didn't have to manually calculate these standards accuracies or any of this. In this demonstration, I'm going to actually walk you through this process and show you how these things come to be. So if we completed our calibration, the next thing we would do is we would need to save our calibration in the database. I'm going to come up here and click on Save Channel. You can see I have some indications here, some red indications indicating potential issues that I'm missing data. We're going to go ahead and hit OK, just again for demonstration purposes. When I come up, this needs to actually be signed. And there are 2 options for sign. Sign not complete. This would be if you're just quitting for the day and you're going to come back and work on it tomorrow, but you want to save it in the database. However, if you're finished with the calibration, you would do sign, complete, and lock. In order to complete the calibration in CMS, the MPS calibration has to be sign, complete, and lock. So I'm going to go ahead and hit sign, complete, and lock. This is an e-signature, so I have to authenticate. Now that the calibration is signed, I'll just hit OK. And then the next step would be to go back to CMS and close out the calibration. But this isn't a CMS demonstration, so we aren't going to actually do that. Our next step is going to be to go to design mode and talk about how data sheets are built and how all of these automatic things that I talked about in the uncertainty model and standards accuracies and everything work. We're in design mode now. The next thing we're going to want to do is go to Edit and enable Edit mode. Here on the right-hand side of the screen, we have our developer workspace, and these are our basic editing tools. In addition to things like manually inserting test points and copying and pasting over here. We'll come back and talk about these. But for our main tools, we have the datasheet properties. This is our datasheet document header, information like manufacturer, model, description, specification reference that applies, and then information about the calibration procedure that's associated with the datasheet. We have our test point builder, and the test point builder is the tool that you'll use for building most of your test points. That is the quantitative test points. We have various properties about the test point. For instance, its specification information. You can see it's 0.015% of indicated value. The full scale value is 200 millivolts, and the full scale error is 0.04%. Test point uncertainty, this is where you actually manage the uncertainty budget. Now, MPS by default is going to be set to use model defaults. And when you do that, it's going to automatically manage the uncertainty budget for you. And we'll be talking about this in a little more detail later. But just know that if you have this on, everything will happen automatically. You don't have to just use the automatic features. You can either turn the use model defaults off and decide which automatic elements, if any, you want to use, and also manually add other additional budget items. The datasheet standards, this is where we actually assign calibration standards to the datasheet. So here we have that 1 meter calibrator, and then here we have these different instruments that can be the meter calibrator. These are selectable options by the user at the time of calibration that we want to support. If we click on this Assign Standards Test Point tab, this will show us the actual standard ranges assigned to the individual test point. When I choose different test points, you can see it's showing me the information for the test point that I currently have selected. So you can see that for this test point, we have one range assigned for each of these supported standard instruments. So for the meter calibrator, the user can select the 5700, and MPS knows that the 220 millivolt DC range is applicable and knows what the specifications are for that range. And then for the 5500, as we talked about, you can see here that TAR, as we mentioned before, is really not an appropriate standard for this. But again, it's in here for demonstration purposes. In red, you can see that 2.5 to 1 TUR to stand out as a warning flag to you. One of the things you might be asking yourselves at this point, okay, so we have range for each of these instruments assigned to the test points. I mean, how difficult is it to do this for every test point in the datasheet? This leads us to a tool that comes with MPS called Metspec. It's a system for digital instrument specifications. Here you can see we've got a Hewlett-Packard 34401 multimeter, and these are its specifications. For instance, if I look at voltage DC, I've got 100 millivolt range, a 1 volt range, a 10 volt range. So if I open one of these ranges, you can see I've got parametric limits for the range, 0 to 12 volts essentially. And then I have two different accuracy specifications, one for 90-day specifications and one for 1 year. And if I click on the 90-day specification, and if you look over here on the right, these are the specification components for it. All right, so full scale is 10, it's percent of indicated value, and it's percent of full scale. Again, we could use floor error and dB logarithmic and equations if necessary for each range. Now, I want to talk briefly about something a little more complicated, which is like AC voltage. Because in AC voltage, just like in the manufacturer's manual, if you look at the specifications, you'll see you have a 100 millivolt range, but then you have subbands for frequency. Okay, and that's how this works in MPS also. Metspec comes with MPS, by the way. It's not something you have to buy separately. We have, I think, about 650 of these that come with MPS, and of course you can create your own. The most important thing to know right now about Metspec are these parametric limits. For this 100 millivolts, 5 Hz, 10 Hz range, you can see there are two parameters. You've got the 5 to 120 millivolts, and then 5 Hz to 10 Hz. These define the parametric limits for the range. And of course, the first parameter is always the quantitative parameter. That's what's being measured or outputted. The second to nth, there were more than one, would be the qualifiers. And the fact that this is millivolts and the qualifier is frequency makes it an AC range. If this were the other way around, if frequency were the first parameter and millivolts was the second parameter, we would be talking about a frequency range because the quantitative parameter would be frequency. The reason I'm going into such detail on this is very important to understand how MPS is actually going to use this information to find suitable ranges for calibration standards for you automatically. So now that you know a little bit about Metspec, What you should know is that these are all Metspec instruments that are assigned to the datasheet. Here we have we pop back to the datasheet standards, we've got our calibrator, and for our 4 supported Metspec instruments, that can be the calibration standard the user can select at the time of calibration. One of the primary uses for these Metspec instruments are as calibration standards in MPS, and that's what they're used for the most. However, if you have a Metspec instrument, you can also use it to build the datasheet for it in MPS. In the test point builder, there's a button where I can choose a Metspec range and have it load the test point builder to actually create test points using the Metspec instrument's specifications. Another important factor when you're using Metspec instruments as calibration standards in MPS is that MPS and Metspec have a units of measure conversion system built into it. If, for instance, I have a test point that was 0.005 volts, and here I have a range that covers 5 millivolts, then it's not a problem because MPS will automatically convert between volts and millivolts. The same thing applies to my frequency band. This is 10 hertz here, but if the frequency in the MPS test point was specified as 0.01 kilohertz, it wouldn't matter because it can convert between those. Now, that doesn't sound like such a big deal, but it gets more involved when you get into things like degrees C and degrees F, which are also no problem because it can automatically convert those. MPS has a tool that's available both actually in MPS and Metspec, a units converter. So if I actually choose, for instance, length, and I choose meters, and then I choose foot, okay, you can see 1 meter is 3.2 whatever feet, and if I enter 2 meters, I see 2 feet. This tool is handy to use, but the reason I'm showing it to you is just to illustrate how MPS does these conversions in real time. If I go to temperature and I choose degrees C, and then I choose degrees F as a target, and if I choose 25 degrees C, you can see that that's 77 degrees F. And this is happening all the time in the background. I won't get into a lot of detail on units of measure, but there is actually a units of measure management system built into Metspec. Metspec manages the units of measure for the MOX system. That's all I'm going to say about this. This is too detailed for our demo, but just know that this exists, and you can add your own units of measure as well. So if you encounter some uncommon unit of measure and you want to add it as a unit of measure, you can certainly do that. And then the last point on Metspec is just a reminder about these parameters that I was telling you, because this is involved in something I'm going to show you in a bit about how MPS can auto-assign Metspec ranges. So now that you're familiar with Metspec, and we've talked about instrument ranges assigned to test points, let's talk about how this is done. So what I'm going to do is I'm actually going to pick a series of test points. So these DC voltage test points, and I'm going to tell MPS to forget everything it knows about these standards. One thing before I do this, you'll notice that we have our TARs, TURs, EMUs, and PFA and PFR, all of that stuff. So when I hit yes, you'll notice that all of that is gone. And the reason that all of that is gone is there's no information about the calibration standards, so consequently, there's no information about them automatically being put in the uncertainty model. So now the question is, how do I actually assign these ranges from the different instruments? How difficult is that? Well, there's an auto-assign tool here. When I click on this for the test point or test points that I have selected, or optionally all test points, if I was doing a simple, say, DMM, and I just wanted it to assign the standards for all the test points at once, I could do that. But here we're just going to work with the selected ones. Now, here we just have one calibration standard, a meter calibrator. And I'm going to select that, and that by default selects all the instruments which I wanted to do. So now when I do this and hit OK, let me tell you what's going to happen. For each test point that's in here, it has its own parameters. Here in this case, there's just one parameter for this last test point, which is the 1,000 volt range, right? So it's 1,000 volts. When I hit OK, what's going to happen is, starting with the first test point, MPS and the first calibration standard instrument here, MPS is going to look at every range in this instrument and find every range that's a parametric match, so essentially DC, one parameter for voltage. And then for every range that's a parametric match, it will calculate the accuracy actually at that specific set point using the spec components stored in the Metspec range. Once it's done that for each of the ranges that are a parametric match, it will choose the most accurate and assign it. Then it will do that for these other three standards, and then it will go on to the second test point and repeat the process, so on and so forth for each of the selected test points. So when I hit OK, you can see it's done. Now it's automatically selected appropriate ranges for each of those. And then now you'll notice I've got my TARs back, my TURs, EMUs, PFAs, and PFRs. When I look at my test point uncertainty budgets now, you can see that the 5522 calibrator is in the uncertainty budget automatically. And if I go back to the standards, you can see that's because the 5522 is the currently selected standard. If I choose the 5500A, you'll notice first off that this test point, its tolerance right now is not guard banded because the 5522 is selected. When I select this standard, the 5500, as the selected standard, you can see that it automatically guard banded all of these test points. And now when I look at the test point uncertainty budget, you can see that the 5500 is now in there instead of the 5522. The blue line that you see here is actually an influence chart. It's just showing the relative weight of items in the uncertainty budget. Now, one other quick thing while we're here for the uncertainty is just to talk a little bit more about these options for the uncertainty model. As I said, we're using model defaults. If we click on Edit for the uncertainty budget, and I choose Turn Off Use Model Defaults, then you can see that I can change which of these options automatically appear in the budget. And the other one is repeatability from resolution. This is one of three ways that you can do repeatability in MPS. And when you would use this is essentially if you have no other information. You want to include a repeatability item, but you have no real data to support it. So this would essentially put in a repeatability item using a one count of the measurement resolution. And it's just essentially like measurement resolution, but with a different label. And then the measurement samples, this is what I was talking about when we were in calibration mode. If this test point is configured for sampling at the time of calibration, the standard deviation of the samples will get added as a type A budget item. MPS also supports the use of degrees of freedom. That's optional. You also have two different types of uncertainty models. You have budget items, which is by far the most common type, and then you also have multiple test point measurement equations, which we'll talk about later. Once you turn off Use Model Defaults, then you can also manually add budget items. So you can add additional budget items, and we're going to come back and do that in a later example, so I won't talk about that now. So now that we've assigned all of our ranges for this standard, we're going to take it up a notch by showing you what happens if you use two standards at the same time. So I'm going to come here to my Manage Standards, and I'm actually going to add another instrument. And I'm going to call it the Monitoring DMM. Normally in the real world, if you had a monitoring DMM or a calibrator, you'd only be really using one or the other as the quantitative standard. But maybe if we were doing something, we were monitoring an output with a DMM and applying a value with the calibrator or something like that. So now I'm going to add a Metspec instrument, and I'm going to tell it to import a Metspec instrument. We're going to use our 8.5 digit DMMs because this is a pretty accurate DMM. Okay, and so we'll hit OK. That was our Fluke 8508. So let's add another one for the Hewlett-Packard 3458. The Hewlett-Packard or Agilent or whatever they're called this week. So let's go ahead and select that. What you choose would actually be what you calibrate yours to. So if you calibrate them to 1 year specs, then choose 1 year. All right, so now I've got those two standards, but you can see that in my auto-assigned standards, I just have the meter calibrator. So now, if I also want to assign to these same ranges that we have selected, those monitoring DMMs, that I just go back to auto assign. I'll just pick the monitoring DMM because I already have assignments for that. So now I pick the monitoring DMMs, hit OK, and now you can see that I have two instruments, and for the monitoring DMMs, I have a range for those as well. But now you'll notice that I have just one of them is selected, and of course, needless to say, only one instrument for each standard can be selected at any given time. So you're only using one. If you needed two calibrators, then you would have two standards. Okay, when I do that, so you can see I've got the 3458 currently selected and the 5500 currently selected. And now if I look at my test point uncertainty budget, you can see that there are actually two budget items in here for calibration standards, the 5500 and the 3458. All right, so that's just how you do multiple standards as well. So now that we have our standards set up here, another thing that we would probably do is we would want to actually look at our standards to see if they're all really a good fit for this calibration. So again, as we said, our Fluke 5500 here, in the real world, we would look at this and say, I've got a 5700 at 18 to 1, a 5520 at 9.5 to 1, a 5522 at 7.6 to 1. If I have those standards, there's no reason that I would actually want to do a calibration with a 5500 unless we didn't have these other standards. So what I would do then, and this being the real world now, is I would choose the 5500 and I would just tell it to delete this instrument altogether. So now when I delete this instrument, it actually gets removed from all the test points in the datasheet. So now if we go back and look, you can see we just have the 3 calibrators now as options. This is kind of a good tool if you have a standard that you're not sure if it's going to be okay or not. You can just add it and try it. If it doesn't have the necessary accuracy, then you can just delete it. So you also have the option, again, to come up here to View and turn off the developer workbench, and then you can see more information over here about the standard. So you can see that this green indicates that everything is good. The red indicates, with these little yellow marks, indicates potential problems. I won't get into the detail on this, but just know that if you see that, then that's just your indicator to click on that test point and then go back to your developer workbench, and then you can look and see that there are issues with that particular test point. Next up, we're going to take a look at some of the advanced uncertainty modeling features. You can see I've loaded another data sheet that just has some different examples of uncertainty stuff that I want to show. This data sheet is really just used for demonstration purposes. It has a lot of different kinds of test points that illustrate different things about uncertainty budgeting. You can see that for this test point that we have 2 gray budget items, and these are the automatically added budget items, and we have 3 items that are in black. These are manually added budget items. And the labels here are just for demonstration purposes to illustrate what they are. In the real world, we would use real practical descriptions. In the uncertainty budget editor, we have the use model defaults turned off. We have some of our automatic items still checked, so those are being put in automatically, like the measurement resolution and the assigned standards. Now, with the use model defaults turned off, we have editing tools show up here for actually managing the budget items manually. We have three types of manual budget items added. One is just a general budget item, and one is manual repeatability, which is the second way to do repeatability, actually the second and third ways, and a manual standard. You don't really have to use Metspec instruments for standards. You can assign standards manually. Also, if you want to have a standard that's going to show up, you want it for some reason to be included in your TUR and uncertainty budget, but not in the TAR, then you can manually add a standard instead of assigning it to the test point. Standards assigned to a test point would be included in the TAR, and standards assigned this way would not. Let's take a look at just a generic manual budget item. I can either click on the edit button or else just double click on it, and it brings up the uncertainty budget item editor. In the error source description, we would give it the proper name for the budget item. Again, we're just using demo names here, manual budget item. And then you would enter the error limit. Then you would choose an error limit distribution, and this includes the more common normal probability distributions. And of course, you can also choose custom probability if you have something other than the standard ones that you're using. You also have other things like Rayleigh, rectangular, triangular, U-shaped, rectangular for resolution. You choose the appropriate distribution, and then it calculates the K-factor for you. And then the standard uncertainty is going to be the error limit divided by the K-factor. And that gives us our K equals 1 value. Now you also would enter in the type, either A or B, or optionally you can leave it blank. If you're using degrees of freedom, this is where you would enter the degrees of freedom. And optionally you can also enter a sensitivity coefficient. The default is 1.0. Next is manual repeatability. This particular budget item is just like our other one, except we're using the repeatability tool. And this gets to my point about the two other ways to do repeatability. The first one I talked about being having it just put in an automatically repeatability from resolution item, which is essentially one count at the measurement resolution. You can also create your own just by doing it like a regular budget item. But MPS also includes a reliability tool. If you have actual reliability data, then you can enter the reliability data from your reliability study for the test point in here, and then you can indicate the number of values used for each item. So if these are averages of 5 or something, then you would put in 5, and then you can have it calculate the budget item for you, the repeatability uncertainty, and it will automatically calculate degrees of freedom and all of that. We'll just hit cancel here, and then I'll hit cancel for this, and then also for a manual standard. Now, there's also a tool for this. You can, of course, just put in an error limit, choose a distribution just like a regular budget item, but there's also an error limit tool that you can use for this. And so the error limit tool has two master modes. It has one if you want to do it from a Metspec instrument, and these are actually separate from the normal calibration standard ones. So you can choose a Metspec instrument that isn't in your list of calibration standards for the datasheet. You can add those here. And it has the same feature to auto-assign, or you can manually assign ranges, either way. And then it will compute for you the error limit based on that and the set point information, as we previously discussed, the way it would do for a regular instrument range assignment. Optionally, you can also just manually enter specification elements like you would for a test point or a Metspec range, and then have it calculate the error limit from that. All right, again, I'm just going to hit cancel. Cancel. Another type of test point uncertainty budget is the multiple test point equation. This I told you about earlier. Said we'd come back to it. Now we're here. So rather than display conventional budget items, you can see that this looks different. This is going to use the input from other test points and a measurement equation to derive its uncertainty budget. Now, the way this works is, in this case, we have volume, and we have another one for area that just uses length and width. Volume, you can see it's length, width, and height. And there are 3 test points, and the 3 test points you can see have just conventional uncertainty budgets. What's unique about these test points is that they have a bookmark name. So you can see the length one, it has a name called length. The width has a name called width, and the height has a name called height. And in the MTPE, for instance, for volume, where we're using all 3 of those, we have a measurement equation. So if we look at the measurement equation, now those unique names I was telling you, like length, width, and height, those are actually become variables in the equation. So the equation for volume is length times width times height. Now, the inputs for these at the time at design time when you're building the data sheet are the nominal values for the test points. At the time of calibration, they're going to be the measured values. So when you're taking as found value, this would be the as found value for length, the as found value for width, and the as found value for height. And they get applied to this equation. And then MPS will also calculate the sensitivity coefficients using partial derivatives from the 3 input test points. You also have the option to use optional correlation with these to correlate these different uncertainty budgets together. So if we click on the correlation tool, you can see we have a correlation matrix here for our length, width, and height by our length, width, and height. If I click on one of these, then you can see that the measurement correlation analysis will always have the variable 1 will be essentially this one, the width, and then the variable 2 would be length in this case, right? It's this one by that one. So 1 is length. So width and length. And then these are the budget items that are in there, and MPS will automatically associate the budget items in the correlation matrix. And we won't really get into detail in this here in the demonstration, but just know that if you don't want to go this far with doing an actual correlation analysis for the inputs, you can always do like this one does, which you notice that this has A and A, which means they're derived by analysis, and this one has M, it's set manually. So you can always click on the manual entry for one of the items and just enter a correlation value if you want to do that. Another really cool feature for the uncertainty system is the ability to generate an uncertainty analysis report. So if we click on this button up here, we can decide to do this for either just the currently selected test point or all test points. And I'll pick all test points. It generates a report that shows me information about the uncertainty budgets for all the test points. So, if you get audited and the auditor wants to see information about the test point uncertainty analysis, then you can generate this report. You can also put in rich text comments, both at the datasheet level and for individual test points if you want. I'm not going to demonstrate that. I think you get the point. And so at the top, we have information about the datasheet document itself. And then for each of the test points in the datasheet, it shows the test point here. If we come down and look, for instance, at this test point, you can see it's a 10-volt test point. This is the tolerance, the tar, tur, and EMU. And then, we've got some notes here. And then it actually shows the uncertainty budget items. So these are the descriptions, the error limits, the error limit distributions, the types, etc., etc. And here's the combined uncertainty of those. Our uncertainty confidence, effective degrees of freedom, we're using degrees of freedom in this case, the coverage factor, and the expanded uncertainty. Of course, when you use degrees of freedom, the coverage factor is modified based on the degrees of freedom. Okay, and then our risk information. So in this case, we're not guard banded, so it's just showing our standard PFA and PFR using the design tolerance. Now, if we go to another test point that's guard banded, such as this test point, you can see it's actually guard banded. And then for this one, we actually, in the risk, it also shows the risk with the design tolerances and the risks with the guard band tolerances and the guard band method used. So if we look at our volume test point, which was a multiple test point equation, you can see it looks a little different. Same basic information about the test point, but then here instead of a budget, it's showing our input test points and that information about that, including the sensitivity coefficients of the inputs. And then it includes our correlation matrix. Two of these three are actually done by analysis, so the analyses for each of those is also shown here. Now, one of the neat things about this report is that this is all rich text, so you can just copy this content and you can paste it into Word or whatever you want to do, or if you want to send somebody an email specifically about one of these test points, you can do that. Here's an example. I highlighted this and copied it, and then we can go into Word and just paste that. So another feature for the uncertainty modeling is a lot of time you have a series of test points like this where the uncertainty budgets are all very similar. Right, you're going to have essentially the same budget items when you're doing manual budgets, but the error limits, let's say, are going to be different. You can select a test point, and then you can come up here and copy that uncertainty budget, and then you can go to another test point and paste that uncertainty budget, like so, and then you can go in and just manually edit the error limits for them. It just helps save a lot of time so you don't have to manually re-enter all this information. Next up, we're going to talk about calibration history analysis in MPS. So I've loaded a datasheet for a Hewlett-Packard 34401 digital multimeter, and I've loaded the calibration history for it. Here you can see this is all the actual measurement history for this datasheet. Now, when I click on different test points, as with everything else in MPS, you can see as I move down through different test points, I'm seeing the measurement history for that particular test point. Across the x-axis here is time. So this being the oldest calibration, these being the most recent, the center line being the nominal or set point value, and the red line up here is the upper tolerance limit, and this is the lower tolerance limit. So one of the key factors is that MPS actually has document identifiers in the test point that get applied to measurements that are made. You have an unbreakable link between measurements made and the source test point. That's how MPS knows how to associate all this measurement data with this particular test point. If I just want to see as found data, I can come up here and just uncheck as left, and now I only see my as found measurement data. You can also filter, for instance, by asset ID, and then now I can look at the calibration history for just different specific assets. So when I choose those test points, also you can do it by who actually did the calibration. And this is useful sometimes for physical dimensional type equipment where you have different people, maybe their technique might be better than others, so you can look for issues associated with that. We can also do interval analysis for this particular calibration, and I'll do it for this asset I have selected. By the way, when we were looking at approved by, you notice these are all like user 11 different user limits because this is a demonstration database, so we don't have real people's names in here. So again, going back, picking an asset, and then we'll go to interval analysis report, and it's asking me if I want to include measurement history. I'll say yes, and hit OK. And then this report comes up, and this is showing me what my current configuration settings are, my reliability target, my minimum and maximum allowed calibration intervals, my interval change confidence, and for the instrument as a whole, in this case, I just have 6 calibrations. And the average interval, again, just one thing I need to mention as we go forward, that this is a demonstration database, and a lot of the data that's in here is really old and it's kind of interrupted. So you see like the 512 days, that's based on the interval between calibration. So again, this demo database is going to be kind of spotty for that. Our average here is 512 days. Our longest interval is 720. And then the number in tolerance was 6. And observed reliability is 100%. And the recommended interval is 512 days. And this is using the A3 interval analysis model. So with those settings, the threshold for increasing the interval is pretty high. And 6 samples is probably not enough to do it, even though there are no out of tolerance. So this is also showing me my apparent reliability, my upper and lower confidence limits, the average number of tests per year, and then for every individual test point in the datasheet, it's also going to show me an independent analysis just for that one test point, as though it alone was a sole document having interval analysis performed on it. Here it's showing me the actual measurement history for that particular test point. And what the purpose of doing this for individual test points is that you might find that you have a situation where your recommended interval is shorter than it could be. And that may be contributed just by a couple of test points. So you may have a couple of test points that have a disproportionately high failure rate or low reliability. And in which case, if you could do something with those test points, some type of limited calibration or derate the specifications for it or something, you might very well be able to lengthen the interval for the whole thing. And that's the type of information that you would look for in the calibration analysis within MPS. There's another tool called the MOX statistics miner that actually performs interval analysis on all of your data sheets in the background and will produce summary reports. When you would come in here and look at it in MPS, is if you spot something in one of those reports and you want to take a deeper dive into it, that's when you would come in here and look at the detail. Up next is the calibration history analysis execute range usage report. This is an advanced form of reverse traceability. Now, what I've done, I loaded an actual calibration this time instead of a datasheet for a Fluke 5700 calibrator. We're looking at one of the test points from that calibration at 200 millivolts at 1 kilohertz. Now, the as found data here is 8 parts per million, minus 8 parts per million, and the tolerance is 130, so it's not even close to being out of tolerance. But we'll assume for the purposes of demonstration that it was. Now, one of the things that we would need to do is we would now need to look and see how was that calibration, this particular range of this calibration standard used in the performance of other calibrations. I'm going to tell it to execute a range usage report. When I click on the execute range usage report, so I'm going to tell it to include test point specifications also, and then run the report. Now, what this report shows, and let me make this a little bigger, this report is a MOX instrument range utilization report specifically for asset S1 to 01687. It's a Fluke 5700 EP calibrator with 5725 for the AC voltage function, 220 millivolts at 40 hertz to 20 kilohertz range for this period of time. And what this report is going to show me are all of the calibrations that used this specific range of this specific asset of this calibrator in this time period. And what that's going to allow me to do is to see if there's any potential impact from this failure. What this section is showing me here is these are calibrations that were performed. And again, this is demo data, right? So we're looking at 2010, that kind of thing. These are the test points from this calibration that used this range of this standard. And this is showing me the as found and as left measured values, what the calibration tolerance was, and what the actual test ratio was, 600 to 1. So, again, unless this standard was really way off, it's not going to have an impact. So I can look at, and I won't go through a lot of these in the interest of time, but just so you can look at different calibrations that were performed and make the appropriate assessment. All right, so I will hit close. Next, I'm going to talk just briefly about the MOX statistics binder. This is, I mentioned a little while ago, is the tool that does the actual data mining en masse. So this tool also comes with MPS, and what its purpose is to actually mine your database for all MPS datasheets and to perform interval analysis on all the data, store the summary results from those analyses in a database that you can view reports on to find, for instance, items that have recommended cal interval changes and all of that. And if you have MOX CMS, it also performs the same analysis on make models in CMS. And the CMS one differs from MPS in that it's really just based on the essentially go, no-go condition of the calibration as a whole. So before you run the analysis for the first time, you'll want to go under Administration, and you'll want to configure the interval analysis settings. And this is just telling it, interval change, confidence, reliability, target, etc., etc. I won't go into detail in this. So let's just go ahead and start this running, and I'll talk a little more about it while it's running. We're running the MPS analysis right now. So for every data sheet in the database, it's opening that, and then it's looking at all of the measurement history. It's loading all of the measurement history in memory, and then it's doing an analysis for the entire, essentially, make model. So it does one analysis using all of the data from all calibrations, and then in memory, it subfilters and does separate analyses for individual assets using only the data from those particular assets. And if you're using CMS, it links to CMS also to do make model, as I talked about for calibrations in CMS. But it's very similar to how the MPS one works, and we won't get into the details of the differences in the analyses in this demo. I'll go ahead and just stop this. So I just wanted to give you a sense of what it does. And it does this in the background. So you would essentially start this and then go about your business and just let it run the whole thing. If you have a data sheet with 1 year specifications and a separate data sheet for 90-day specifications, then it's going to be separate analyses for both of those. So, it's apples and apples. Whereas with CMS, it's based on the make model. It's the more simple, conventional type of interval analysis where it's just go, no go for any calibration in the make model. You can come up here to Reports, and then you can choose either to view CMS analysis reports or MPS analysis reports, and choose the type of report you want. So in this case, Delta Cal Interval Summary, this is going to be a report about recommended interval changes. And then you can sort it many different ways, for instance, by make model. And you can also use these filters to tell it only show me items that have at least 5 samples, and or where the recommended interval delta is greater than 10 days. If we actually do this report, and I'll make this a little bigger so you can see it, you'll see we have an interval analysis report that looks kind of similar to what I showed you in the calibration history analysis in MPS. Only difference is that we're going to get multiple different data sheets showing up in here. So you can see this first one is for a preset torque wrench, 60 pound-feet, and it's going to show me essentially that same type of information: average interval, longest interval, number of tests, number in tolerance, and observed reliability, and a recommended interval. And if it's green, that means it's an interval lengthening. If it's red, that means it's recommending shortening it. This item here for this 100 PSIG grade 3A pressure gauge, this actually shows an example of how this report might guide you into going into MPS and bringing up the data. Here we actually have it recommending the interval be shortened. We've got average interval is 321 days. The longest interval was 364. Number of tests were 60. But of those, 13 of them were out of tolerance. So consequently, we have an observed reliability of 78.333%, and we have a 246-day recommended interval. Now, if I wanted to go and investigate this particular one further, maybe look at the different test point information and all that stuff, that's where I would go back into MPS and bring up this data sheet and load the calibration history, and then dive into the more detailed report there. So this is just an example of how you would use this report to actually help you assess your situation with calibration intervals. Other important features in MPS include administration. You can configure MPS to set your particular uncertainty model targets and things like that, your uncertainty confidence, and various other settings and configurations that control different behaviors in MPS. You can manage users, create users, grant them access. MPS is a permissions-based system, so users need to actually have permissions to do different things in the system, and you control all of that by managing users and having roles and assigning users to roles. MPS has a full audit logging system, so every time you approve a data sheet as either a new data sheet or a revision of an existing one, there are audit log entries made. The same thing for Metspec instruments, when you approve those into the database, and you can do audit reports on all of that stuff. Next up, we're actually going to build a data sheet from scratch. So the first thing I want to do is I want to go to File, Data Sheet, New Template. We're going to have a new empty data sheet, and I'm going to want to go to my design mode. We're already in edit mode when we do a new data sheet, so I don't have to select that. And now we're ready to create a new data sheet. The first step in creating our new data sheet would actually be to edit all of this document header properties. If I click on edit here, this is where I would come and put in my manufacturer, model number, description, spec reference. And spec reference is critically important because when somebody comes back to view this later or audit it, you need to know where these specifications came from. And then calibration procedure information. And if you have our CMS system, if you purchase the CMS system, you can actually link this to procedures in CMS and it'll fill out this information for you. There's other sections in here, but we aren't going to get into that. And I'm also not going to fill this out for now just to save time. You don't need to see me type in fluke, yada, yada. So the next step will be to actually create the test points for our data sheet. And that takes us to the test point builder. There are a few different kinds of test points. There are manually created test points, and those would be for things like just labels or simple test points where it's essentially a go, no-go type of scenario or pass-fail type of scenario where we're just going to type information in. But the vast majority of your test points will be created using the specifications as a base in the test point builder. First, we'll create a couple of manual test points just so you can see how that's done. The first thing I might want to do is just add a label to say that this is going to be our DC voltage tests. And then the next test point that I want to have might be a pass-fail type test point. We'll call that display tests, and then for a pass-fail type test point, you need to have something in the nominal value. And actually, if I turn off my developer workbench here, you can actually see our test point configuration. So you can see the first test point, it doesn't recognize that as really being anything because it's really just a label. But for this one, let's put in pass as the nominal value. And then for the tolerance, as soon as I entered one character in the tolerances, it recognized it as being a simple text type of test point. And a simple text type of test point just means it's not quantitative. At the time of calibration, the user can enter a value and there'll be a checkbox to indicate if that meant pass or fail. Now, if I actually finish what I was doing here, and I just include the words pass and fail, and it doesn't matter what order they're in. It could be fail, pass, pass dash fail, whatever. But if the words pass and fail are in the tolerance, then now MPS recognizes that as specifically a pass or fail type test point, which would allow me to actually enter measured values of P or F for pass or fail when I actually do the measurements. Now that we've done that, we'll create our actual quantitative test points using the test point builder. So in all of our examples so far, we've been talking about electrical type equipment a lot. So let's make our actual data sheet here be a pressure gauge, just do something different. So what I'm going to do is I'm going to tell it I'm going to use multiple test points. We're going to specify several test points all at once. And these are all going to be entered as fixed points. For our pressure gauge, it's going to be a 150 psi gauge. So it's going to be 25 psi, 50, 75, 100, 125, 150, and then 125, 100, 75, 50, and 25 back down. I need to enter my units of measure. I happen to know that it's PSI, so I can just enter that. However, you should only type them in if you really know it. And the truth is that when you work with the system, you do pressure gauges all the time, you're going to know them. If you don't know the units of measure, you're not positive about the units of measure, you have a couple of tools here to help you. One is just a lookup for the units of measure. If I typed in PSI, also, if you're doing more complicated test points with multiple parameters like an amplitude and a frequency, and you're not sure how to do that, again, it's always done the same way. So once you get used to it, you'll just probably type them in. But there's a wizard here to help you with that, right? So you can add additional qualifier parameters, and it will help you set them up and everything. But we don't need to do that. Now we want to enter our number of decimal places that we want to have for our tolerances and nominal value. So I'm going to enter 2 decimal places. Then we select the tolerance display format. The default is low to high, which is 99.1 to 100.9, that type of thing, or plus or minus units. This gets used a lot with dimensional stuff, right, where it's plus or minus 1 microinch. We'll just go with our standard low to high. The specification type is going to be either symmetrical, asymmetrical, or one-sided. If I choose symmetrical, that means I just need to enter one spec value because the high and the low are the same. If I choose asymmetrical, then I can specify a different low tolerance specification and high tolerance specification. And if I choose just one-sided, then I can use one of my operands. So greater than, 10 millivolts or 100 psi or whatever it is. But we're just going to use symmetrical for our pressure gauge, which is common. For our spec components, because this is pressure, we're going to be using percent of indicated value only. You can use any of these in combination, and the reason for the question marks here is because this could be percent or ppm. So either percent or ppm of IV, percent or ppm of full scale, a floor error, and the floor error would be plus or minus a unit of measure, or like 1 count, that type of thing. Plus or minus dB, if we choose that, then we can specify whether it's linear, volt amp, or power. It's just the equations, the logarithmic equation that's going to get used for that dB type, or custom calculator. Now, a custom calculator, that's actually going to be based on an equation, or actually could be multiple equations. So if we add a custom calculator, and I'll just load one here. This particular custom calculator has an equation where V would be the input value for the test point. So if we were doing 99 millivolts, this variable would get 99. So if V is greater than 500, then essentially, we're going to add something for every volt above 500, else 0. So if it's not above 500 volts, then it's not going to have a contribution. If it is, then this equation will determine what that contribution is. All right, so I'm just going to hit cancel. We're not going to use an equation for this. Doesn't apply to our pressure situation. Let's go ahead now and make our percent of indicated value. So we're going to use 1% of indicated value for our test point. Now on these spec components, you can actually use any combination of them together, right? So you can add the different ones, including the equations, and what it does is it will basically compute each of them individually, and then the sum of all of these individual error contributions will determine the overall error for the test point. But again, we're just going to use our percent of indicated value. Now let's go ahead and append our test points, but before we do that, because we were changing things with the one side in the operands, it turned off my multiple test points. So let me turn that back on. And then now let's append our test points. And the function tested is going to be pressure tests. And this is just meaningless text. It's going to be essentially the label for the function tested cell. And then the test point step number, this also is meaningless text. This is really just associating it with the step number in your calibration procedure. But it's just text to MPS. So let's say it's going to be 4.2.1. And then over here, we have some more important things. For instance, where is the measured value going to come from at the time of calibration? Obtained from direct entry one value, which is the default. That means the technician is just going to enter one pressure value, and that's going to be the measured value. We could tell it mean of samples. So for instance, if we were doing a pressure gauge, right, and they're going to do essentially 3 clicks, and the mean of the 3 clicks is going to be the measured value. We could choose mean of samples and then specify how many samples are required. Or we can also do calculated prompt. And calculated prompt is another case where we would use a custom calculator, as I showed you before. Let me just open another one that would be an example of that. And let's do Ohm's law. Okay, so this one is going to actually, when it goes to do this, it's going to prompt the user to enter a resistance and a voltage value. And from that resistance and voltage, it's going to calculate a current. And the result of this custom calculator, this equation, is going to be the measured value. And then, again, I'm not going to get into a lot of detail on the editor and stuff for this, but you can actually view an example. This is what the user would actually see pop up. So instead of entering a value, there would be a button they click on, and when they click on the button, they're going to see this form. And you can put in text and stuff to describe, what you want them to enter. All right, so I'm just going to hit cancel. We don't want any of that. We're going to go back and just choose our direct entry one value. Now, this is another really important thing in MPS, the reference value. By default, use the nominal value. So this is a 1% pressure gauge. We're probably just going to use a pressure calibrator for this. So we're going to assume whatever the pressure calibrator says is the true pressure. So we'll set that to whatever our set point is, and that will be what our reference value is also. Now, in more accurate stuff, or happens a lot in temperature, we need to use a separate reference value. So for instance, in temperature, we set the bath to 250 degrees C, but the bath's not really ever going to be 250 degrees C. So we have a reference SPRT in the bath with it, and what the reference probe, the reference thermometer indicates, that's what the actual true temperature is. So if we select this option, then at the time of calibration, the user is going to have to, before they can enter a measured value, they'll have to enter this reference value. And this is another important thing about MPS, because the way it works is the as found and the as left measurement are completely independent. As I showed you in our example when we were doing the calibration where we used different standards, the as found and as left values, they can have different measurement uncertainties, et cetera, well, they can also have different reference values. And whenever you use this option, when the user enters a reference value, MPS will automatically recalculate the tolerance around the reference value that they entered. It'll recompute the standards accuracy, the EMU, TUR, everything around that reference value. And it can be completely independent for as found and as left measurements. All right, and then of course we also have the option for a calculated prompt, right? If we're doing a high accuracy current, we might want them to enter a true value for resistance and a true value for voltage, and the result of the equation is going to be the true value for current. But again, in our example, a 1% pressure gauge, we're just going to assume that the what we set the calibrator to is the nominal value. So we'll just hit OK here, and then here are our test points created. Now, if I just turn off my workbench and I scroll over here, you can see that it actually put in also a human readable version of the specifications and what my 4:1 requirement is for the standards. What happens behind the scenes, let me bring my workbench back up, is MPS actually keeps, if I click on any of these test points, let me clear the test point builder just so you can see we're starting from scratch. If I click on any test point and click on this test point button, it will reload test point builder from the specs. MPS actually embeds the atomized components of the specification in the test point because it has to dynamically recompute this stuff all the time. For instance, at the time of calibration, if you enter a different reference value. So the next thing that we would do is we need to tell it about our calibration standards. So I'm going to add a standard, and this is going to be a pressure calibrator. When we add these standard names, you want them to be readable to the technician. With our pressure calibrator selected, we're going to come down to our Metspec instruments, and we are going to add a Metspec instrument. And, I didn't really mention this before, but when we were in Metspec, but it really works the same way in Metspec as it does with the MPS datasheets. You've got this catalog that's going to look them up in the database. This is going to be a CPC something or other. So CPC 6050 pressure calibrator. I'm going to hit OK. And then now we've got that instrument selected in here. So the next step is going to be to actually assign ranges of the calibrator to all of our test points. So we go to Assign Standards, Test Point, and then we use our Auto Assign tool here. In this case, we're going to tell it to do all test points. And we're going to pick our pressure calibrator and hit OK. And then now, if I just scroll this over a little bit, you can see that we have on our status flags, we have one standard assigned to each test point, and they're green, which means they all meet or exceed our N/1 requirement for TUR. So if we, again, looking at this 150 PSI test point, we have our pressure PSIG units range 0 to 235 PSIG, and here's the spec. And then if we look at the uncertainty budget for it, you can see that we've got our Menser CPC 6050 pressure calibrator in here, along with our budget item and our measurement resolution. And so at this point now, we would be done with designing this data sheet. If we weren't finished with it, we were going to come back and work on it tomorrow, we could always go into File, Datasheet Template, Export Template to File, and actually save this as a disk file. When it's finished, we would want to approve the template to the database. Now, this is approving the template is permission-based, so you have to have the necessary rights to approve the template. And the way this would typically work, if you don't have the rights, you would send this file to someone who does, so they could load your datasheet from a file, review it, and then approve it. And part of the approval process actually puts it in the database. And so I can approve it as a revision or approve it as a new data sheet. This would be a new document because I created it from scratch. A revision might be if I took a data sheet for an existing like item and just modified it, or I fixed an error or something on it. Somebody entered a spec wrong, and I'm doing that as a revision of the existing data sheet. But in this case, it's going to be a new one. So we would click on New, and then I would basically sign it, and I'm not going to do that because I don't actually want to approve this in my database. But once we did, then this data sheet would be in the database, and we can use it to perform calibrations. Having completed creating our new data sheet, next we're going to talk about automation scripting in MPS. Automation scripting in MPS is different than in most systems in the sense that it's additive. You don't have to do any type of automation scripting to do a normal calibration. For instance, if you're doing a data sheet for a micrometer, there's really nothing to automate, right? That's going to be manual. So you don't have to do any automation scripting for that. If you get a new make model digital multimeter in and you create a data sheet for it, then you can go ahead and start calibrating with it. When you get enough of them that it's worthwhile, then at any time you can take that existing data sheet and add automation scripting to it. Automation scripting in MPS can actually take multiple forms. You could have, as I showed you when we started this demonstration, an automated data sheet that is completely automated. It communicates with both the unit under test and the calibration standards via GPIB, RS-232, USB, or Ethernet. It can display instructions to the user, display pictures. You also can have semi-automated calibrations where we're communicating, say, with the standard, but the unit under test, we're going to prompt the user to enter measured values. Could be process type calibrations where we're just going to do things like maybe in temperature, where we're going to ask the user to enter some values, perform some calculations, and the result of those calculations are going to be the measured values. We could be importing data from external systems. So you might have some software that generates a text file with data, and you want to read in that text file and parse it and use that as measurement data in MPS. And you can also use datasheet scripting to actually create new data sheets, which I'll be showing you an example of that in this demo. Automation script editing in MPS is actually done in the calibration master mode, not the design master mode as you might normally expect. The reason for the automation scripting being done in the calibration master mode is we need access to the measurement data and calibration channels and all of that to actually test the automation scripting. So in the calibration mode, over here on this tool, this is the automation editor. And you can see we have our script commands for these test points and our various tools here for actually editing the automation script. Every test point in a data sheet has what amounts to a script procedure. And if you create a new data sheet, they're always there, but you don't have to use them. And that's where you add automation commands to automate that particular test point. Most test points will have very few commands in them because usually the only thing you're doing is calling procedures. And in a large data sheet, you may only have 2 or 3 test points that you're going to do any automation scripting on. So you may only have script commands in those particular test points. Or it could be more complicated where you could actually navigate through an entire data sheet doing a fully automated calibration. But as I said, most of what you do in the test points for the script commands is pretty much calling procedures in other reusable script modules. So here we're executing a sub procedure, and we have the meter calibrator reusable script module, and it has a bunch of different procedures in it that we can call. So set output to parameter, it's going to read information from the set point parameters for the test point and build the actual GPIB commands for the meter calibrator and then issue those commands. These script modules can actually be saved as independent files and reused in other datasheets. Going back to our datasheet here and the test point commands. So unless script commands are very simple, they'll usually have wizards to help you set their parameters. In the case of like this sysimage instruction command, if we single execute just this one command, this shows what the command does, right? It displays instructions and gives us a picture to display what that looks like. If we double click on this command to edit it, the commands have parameters, and these parameters actually control properties of the command. And unless they're very simple, like just assigning a value to a variable or something, the commands will usually have wizards to help you configure the parameters. So in the case of this image instruction one, it wants an instruction. Here I can select one of my instructions that are in the datasheet. I have the editor tool here to edit the instructions. If I wanted to have a second image in here, let's call that figure 2. And we'll just choose a different one like this DC 10 amp. And if I want to view that, I can. So then if I hit OK now, it actually updates all these parameters for me. And now if I execute this command again, now you can see I have 2 figures in here that I can refer to in my text. So that's just an example of how commands are work and edited. It's really beyond the scope of this demo to get into more detail on how automation scripting is done. It would be a separate demonstration if you want to get into detail on that. We'll wrap this up with a couple of actual examples of automation script being used in MPS. In MPS automation scripted datasheets, you can always tell the various places that you can start from by the teal over here in the step number column. So that indicates a place you can run from. You also know because the run button becomes enabled there. We'll go ahead and execute this datasheet for the semi-automated calibration for the Fluke 77 DMM, where we're going to communicate with the calibration standard by GPIB, but the unit under test itself doesn't have an interface. So we'll go ahead and hit run. And you can see it comes up with our instruction for the pass-fail test criteria. To test the display, turn the UUT on and check whether all display segments come on as indicated on LCD display. And these instructions in MPS are RTF or rich text format. You can edit them either in the MPS's RTF editor when you create the instructions, or you can edit them in Microsoft Word and paste them in. So we'll go ahead and select pass. And then next it's going to actually come up with my instructions and image on how to connect the equipment for the DC voltage test. So I'll hit continue. And then now, because this is semi-automated, it has to ask me for the measured value. So it's showing me what the set point is and the tolerance. So let's do 2.699 and hit enter. And I'm just going to halt the script. We just entered one test point. There's no point to continue doing this. You get the idea. I've loaded another datasheet. The purpose of its automation scripting is to build a datasheet. The first time I run the datasheet, the script commands are going to prompt me for specifications for a torque wrench, and then it's going to set up all the test points based on those specifications. Before I start that, you can see that all of these test points are all 0 nominal values, 0 tolerances. Let's go ahead and run this. And my units of measure are pound-feet. I could select different options. My full-scale value, let's say, is going to be 250. My full scale spec is going to be 0, and let's just say it's 1% of indicated value, no floor error, and we're going to use 2 decimal places. And then for my counterclockwise specification info, it's going to default to the same as clockwise, and that's fine. So I'll hit OK. And then now it's asking me for boilerplate information. This is where I would put in the manufacturer, like Snap-on, the model, like, TQS 250 or whatever it is. I'm not going to actually do that in this demo, just in the interest of time. And you can see that it actually created all the test points here for my torque wrench. Now, when I actually run this datasheet scripting again, now that it's created the datasheet, it's now a calibration scripting. It's asking me for the 3 breakpoints, and it's going to fill those in. So I'm doing a 50 foot-pound, so let's just do 49.98. 49.97 and 50.01 and hit OK. And again, I'm just going to halt the script here, but you can see it's putting in my measured value, and I can approve this data sheet once I've used the scripting to create it, and then now it has the automation scripting left to just do the calibrations for it. Okay, so that's another example of using automation scripting to actually build new datasheets. So one other thing I want to point out on this datasheet before I leave it, you can see that we actually have our sampling section showed up. Earlier in the demo, I told you that when a test point is configured for sampling, a section would show up here for entering the samples, and here it is. So that's because these particular test points are configured to take the 3 clicks, and we're going to use the mean of the 3 clicks as the measured value. Another really powerful feature of MPS automation scripting is its ability to communicate with external applications via COM, such as Excel, or you can create your own plugins to extend MPS's capabilities, and as long as you add a COM interface to them, you can communicate with those through automation scripting with MPS. This example is actually just going to demonstrate MPS communicating with Microsoft Excel. I'm just going to push this down here, and then I'm going to go ahead and run this. And when I do, MPS is going to actually launch Microsoft Excel. So here you can see that we have Excel. Basically, we have its instructions telling us about how it's going to use Excel and all that, and we are not going to read all that now. And then it's asking for the Excel spreadsheet that we're going to use. And then now it's actually loading the Excel application. And this takes a few seconds because Excel is a pretty big application. Although when it first loaded Excel, you don't actually see it because Excel's visibility property is set to false. So now MPS comes up, and it's giving us a couple of options about how frequently we want it to iterate. This is just going to run in a loop, and it's going to pass a couple of values to Excel. Excel is going to use those values to do a bunch of calculations, and then it's going to return 3 values. And we're going to display those 3 values while it's running. And then it's just asking if we want Excel to be visible. We do in this case because I want you to see what it's doing. So let's hit OK. Let me get this down here to where you can see it. And now let's bring Excel back up here. Okay, so what's going on here is that MPS is just basically incrementing these values, these 2 values, and it's basically passing them to these 2 cells in Excel. Excel is doing a bunch of calculations on those values, and then essentially this green value and the 2 black values you see here, MPS is reading those values back from Excel. And so you can see all this updating very, very fast. So the point that I wanted to make with this is that not only can MPS communicate via COM with external applications, is that it does it extremely fast. So that's going to be it for our demo. Thank you very much for spending time with us. I look forward to working with you.